An internship that I took while at Purdue University was with MLMK Steel in Indiana. This was a mini mill producing steel. A mini mill describes the fact that the hot strip mill, as well as the melt shop, were on one site. As an intern, this was a fantastic opportunity to see the whole manufacturing process of steel, rolled steel, in one place. I wasn't pigeonholed into the melt shop or in the hot strip mill. As a mechanical engineering intern, I was given free rein to go and learn about all aspects of the business. One big project I took on at the steel mill was with the electric arc furnace. I like to describe this in very simple terms. It is the most awesome, largest bowl mixer, just like in Mama's kitchen, that melts metal, prepares metal, and gets metal of a consistent quantity and quality before passing on to the next pour-in melt shop operation. Now, these electric arc furnaces are the whisk. There's an arm that drags it back to a stanchion, and this stanchion raises up and down. These electrodes are a set of three. The three electrodes must remain the same distance from each other to have the most efficient mixing, to have the most controlled mixing, and the most predicted mixing of the molten metal. Over time, due to the massive weight, the mass of these electrodes, that whole arm system, that vertical, horizontal, vertical, comes out of line. This previously was done as a maintenance task. This maintenance task was completed periodically, sporadically, and without knowing when it's going to come next. This meant there was large cost. Unpredicted maintenance meant there was unpredicted downtime. Downtime means there's nothing being produced, which meant there's no value added. With a preventative rather than a reactive maintenance plan, we were able to go back in history of when these checks were done, create a schedule for running checks, as well as understanding and backwards engineering, redesigning, and CAD modeling the CAM systems of these three EAF tiers, these three EAF arms. We were able to model, suggest, and come up with a preventative maintenance plan. This preventative maintenance plan reduced the downtime by approximately 15 to 20%, as it was predicted when the maintenance was going to be done, so the materials could be ready at that time. It also meant that scheduling was easier. We knew that in 2 weeks we were going to have to shut down the EAF, so we could plan our business around that. Additionally, we could bring forward that maintenance so as not to impact a bigger job. A smaller technical task that I took on around that EAF, the electric arc furnace, was to do with the sandhopper. When initially installed, a sandhopper was provided to match the EAF. This sandhopper was filled with a sand-like material which could be poured into the molten metal to make sure that the composition of the metal was of a quality as specified, and it was predictable and repeatable. This sandhopper was not used, and it meant that the operator had to go right up to the EAF and split open a bag. This was a dangerous operation, it was uncomfortable, and it was also a lot less accurate. Arguably, it also introduced contaminants. The bag material could have also entered the EAF. What we did, we worked with bearing manufacturers initially to make sure that the movement was right, because we knew that per the original design, strength, weight-wise, it was strong enough to hold. I modeled retrospectively the sandhopper into a digital format that was not there previously, so that we could manipulate it on screen before requiring any manufacture of parts. We worked with bearing manufacturers externally as contractors to come up with the best design, allowing this large piece of steel to work in our application. Particularly where there's such high heat involved, it was really important that the design was correct and verified by our lead engineer.